Hello, folks. Welcome to Rational Science. And I hope my transmission is okay. Everybody's receiving my noise and my images. Anyways, I was going to talk about magnetism today, but I think I got to postpone that because something else came up, which is the subject matter of today. Anyways, let's get to it because we got a long day here. As I said last week and even the previous week, the circus came to town over here. And we had Circus CERN. These folks, they came to town. And it turns out they haven't left. They're still here. And they came with all their show, their clowns. Okay. And so what are they up to? Well, these folks bring their slapstick comedy and so on. You know, they do some of this stuff. They work with the bosons, right? That's their slapstick stuff. And so, yeah, they brought a lot of questions and comments. And so today I got to answer all these things that they raised. Now, you know, when you heard one, you heard them all pretty much, right? But anyways, you see, they've got this slapstick comedy act, the bosons do. And you wonder, you know, what is a boson? Supposedly it's a particle. Okay, that's what they say it is. And it turns out that, we all understand what a particle is, a little ball, right? And so you say, okay, I understand that. It's a particle, it's a ball. That's what we're going to be moving around, etc. Turns out that, they do juggling and they say they're doing these boson balls, right? And you say, okay, I understand that. That's straightforward. You know, that's what their act is all about. But it turns out that, when you look a little deeper, those are not balls. They're not particles, they're not corpuscles, not the traditional ones. So you say, well, hold it, what are they doing their slapstick with? And it turns out they're doing slapstick with concepts. They've got these things rolling around. They have fields and energies and who knows what, waves. And you say, well, is that the same thing as a particle? Is that a corpuscle that I'm staring at? And no, these are concepts. That's what they do their juggling with. Turns out that their jugglers then end up being actually mimes. They have absolutely nothing. That's what they're doing their slapstick with, nothing. And that's part of their show. That's, I guess, the funny part of their show. That you go in there to see a juggler, you end up seeing a mime just moving around. So yeah, it's a little bit of a problem to understand what the circus is about. It's a lot of fun. It's very funny, and I recommend that you watch it, right? But some people take it seriously. That's where we have a problem when they take it seriously. Anyways, I had this troupe of clowns, Bozo and his group, and they came and visited me again. And again, once you heard one of them, you heard them all. So I don't need to analyze all these people because they all pretty much think the same way. Okay, so I'm going to answer one of them, and then another one who is not from the same circus. He's from a different circus. He's from the ether circus. So I'll address them separately. But yeah, they raise a lot of questions, a lot of comments. And I'm going to address those. And almost all of them are related to light. So these are the issues that I'm going to be discussing, in today's lecture. And I want you to keep those in mind throughout the lecture today, okay? The issue is, what is the architecture of light? Does light have an architecture? Is there an entity that underlies light? That's the only issue, okay? Now, I was going to talk a little bit about some other stuff, but I think we're going to have our hands full with this alone, based on the number of comments and questions that this individual asked. And so here we have it. Does light have a physical mediator? What do you think? Do you think light is mediated by absolutely nothing? And if it's mediated by something, what is the mediator? Can we say that it's like the establishment holds, that it's transverse waves? Is that what mediates light? That's what they show you, right? And so that's one issue. The other one is it mediated by particles? You know, the bosons. Well, we have a lot of bozos out there, but they say that it's some kind of corpuscle, and they call it the photon. They say, hey, this photon is what mediates light. Okay, a series of them, right? Okay, and then there's a third version, which is that all three of them. Okay, so we have the transverse wave, the particle, and the wave particle. Okay, so you tell me, okay, which one would you choose? Is any of these valid? Can we use any of these to simulate light? That's the issue. That's the main issue today. And one of the problems I have with these clowns, with these bozos, is that they don't understand the question. They simply don't understand the question. They say, we do math. We want to tell you something about values, about the experiments they've done, and what they proved, what they verified, what they falsified. They talk about a lot of nonsense, and all we want to understand, we want to just get them to tell us what is the mediator of light. That's the only issue today, okay? And you'll see where they hit on the corners, and they never hit in the center, that question. Okay, so the only issue, again, is what is the mediator of light? So here's the question, okay? What is the mediator of light? And here you have all these different versions. We have the one-way discrete particles. I put Alhazen, I think that's how you pronounce his name, Alhazen, I call him. Anyways, Alhazen, I think he was 11th century in the Arab world. And he's the one I credit with the particles, not the Greeks, because the Greeks thought that it was like Superman's vision, that the particles emanated from Superman's eyes and go through the wall. And Alhazen said, no, whatever you see, it's sending particles to your eyes. So that's the only reason I credit him. But you know, it's just history, just so you know which one is which. Then we have the transverse wave. The waves were created by, what's his name, Robert Hooke in 1665, but it was Fresnel, French guy, who, beginning of the 19th century, you know, he's the one who really came up with this notion of the transverse wave, trying to explain, you know, with his picket fence, he tried to explain an experiment. Anyways, when he had proposed the transverse wave, Maxwell comes a little later, a few decades later, and he mathematizes this transverse wave. And that's what we have today, or at least what quantum has today. Then you have the one-way packets. I credit Penrose here. He's the only one I've seen that drew it in one of his books. Okay, so I use his wave packet, even though the notion already existed before him, right? Then we have the ether version, and also I think the flat earthers pretty much subscribe to this, that there's some kind of vortex out there. One of the proponents of this was Descartes, René Descartes, but I'm not sure if he's the first one to propose it. Anyways, there's these vortices, right? And exactly how that works with light, I have no idea, okay? And then you have my version, which I'm saying all these years what they've mistaken the transverse wave is with a rope-like mechanism or entity that torques. That's the mechanism. And so there you have the different versions that you can choose. If you have some other version, by the way, there's people also proposing that there is nothing underlying light. And so, you know, if you have another proposal, hey, you're welcome to propose it. And before you can call any of these irrational, you have to define what you mean by irrational. We do define it in this site. We do rational science, so we better know what rational and irrational is or means. And we're saying that irrationality is when you reify a concept and begin to move it around. You turn it into an object. Again, like field or energy, right, wave. And also another criterion is failing to define the key words that make or break your theory. Those are sine qua non. You know, you need to have definitions. And a lot of people think that when you define words, you're doing semantics. And that's another thing you should keep in mind today, okay? Because that's the official version, that when you attack them from a language point of view, that you're doing semantics and you're not doing math, you're not doing physics, etc., right? And yeah, what we're looking for is physical interpretations, mechanisms. For that, you had better have your language straight. That's the way we look at it here. And again, the third one there is the proposed mechanism is unimaginable. Then you have an irrational theory when nobody can imagine it. You know, like moving through the fourth dimension. Yeah, try that. Okay, so these are the things to keep in mind, okay, throughout the discussion today. It's going to be a dialogue because I'm going to present what they asked or what they commented on, how I'm going to answer that. Okay, so here let's start with the first one. What is light? And a fellow says, experiments demonstrate that light is what? An excitation of the field. The field, I guess a football field, marijuana field, I don't know. And the fields carry energy and momentum. Carry energy and momentum. Sounds like he's got a semantic problem. When you talk about that, they say, oh, Bill, you're doing semantics. Well, it looks like the people who are doing semantics are the people who have these words, this language, this jargon, right? And he says, this is not semantics. It's measured in the lab. Well, how do you measure a field if a field is a concept? How do you carry energy? How do you carry momentum? You know, there you see the field on the center almost turns into a particle because the vibration of field is what they call a particle. And a field is a concept. It's a bunch of numbers. That's all it is. Then you have energy over there on the right. And again, is that a physical entity? I mean, that's how they illustrate it, like, you know, a little smog, a little smoke. Is that what energy looks like? I mean, what is energy? What is a field? It turns out that both of them are concepts. And yeah, you cannot carry concepts around. It's very difficult. I tried it. tried carrying love or intelligence. You can't. It's very difficult. And so these people, what they do is reify concepts. When you call that to their attention, they say, oh, Bill, you're doing semantics. Well, who started doing semantics? You or me? Okay, and so here we have the answer to this. Bill's claim that fields don't store energy or carry momentum is contradicted by what? By experiments? What do you mean? Well, see, he's saying that fields store energy. So he's now suggesting or insinuating that fields are physical objects that are storing another object called energy. So they're storing this thingy called energy. So I guess field is some kind of box, some kind of container, some kind of thing. So they treat field as an object. But then immediately he says electromagnetic fields are physical in the only sense science uses that word. And what is he talking about? Concepts. Predictive, measurable, with energy and momentum, budgets that match experiments. So you see, they treat the word field with this duality. They cover both bases. It's both an object and a concept. It's a thing and an abstraction. Okay, this is the problem. And you can see the definitions down at the bottom there. Field, what is it? Values at each point in space. That's what the definition, the formal definition of the word field is for the purposes of mathematical physics, which is not physics, by the way. Energy, the capacity, and it continues after that. And momentum, what is it? Quantity of motion. So far, all we have is numbers. And they're going to be storing energy in that field. What is energy in numbers? So they're storing numbers in numbers, right? And then they're going to carry this thing they call momentum. How they carry it, I don't know, because momentum is quantity of motion. So you can see the problem. It is a semantic problem, and it's the jargon that they use to express their physical interpretations. We got a problem because we're asking for an explanation of how this universe works, you know, why it works the way it does. Please identify this fieldy thingy, this energy thingy, this wavy thingy, you know, and it turns out they say, well, it's a bunch of numbers. When you say, how do you wave a bunch of numbers? Oh, you're doing semantic. It's a semantic attack. Okay. I think they're doing semantic, not me. Yeah, I'm asking the right questions. And here's, he clarifies, this fellow, he says, this clown says, energy isn't physical. Well, that's, I was saying that energy isn't physical. It says what the experiments show, energy is not a thing you can scoop with a bucket, but it is as physical as momentum and charge. Well, yeah, I agree there because momentum and charge are not physical either. Okay, so that's the problem. The problem is he thinks that field, energy, momentum, charge, all these words that he uses, are things, physical. We have a problem because there you have it again. Energy is the capacity, and physical is what? That which has shape. That's the definition of physical. If you have a different definition of physical, hey, I'd like to hear it. I want you to defend your definition because I'm going to attack it. Okay, so does energy have shape? And the question is no. Energy does not have shape. Momentum doesn't have shape, right? You can't talk about charge because charge is a number. It's in coulombs, right? So we have all these semantic words, this jargon that these people introduce into science, and when you question it, they say, "Oh, Bill, you're doing semantics. It's a semantic attack." Yeah, because you got to get your language straight if you want the audience to understand you, and what you're asking for is an explanation, and they're not giving you an explanation. They're saying, "Look, we verified, we proved, we did an experiment, and it was falsified or not falsified or whatever." Falsified to whom? Who do you falsify this to? Okay? And so, give me a second here. Yeah, you can't, you have to attack the language because that's where the problem is. The problem is language. And people don't understand that and say, I came here to do physics, not to do, language. I didn't come here to learn semantics or grammar, English or whatever. I came here to do physics. Well, you can't do physics without language. You need language, okay? So here you have another one. This is another bozo, but one from the establishment, more or less established establishment. His name is Nick Lucid, okay? Some of you have heard of him. And this is what he's going to tell you about what light is, okay? So let's hear it from him. Here it goes. So now you know. They're particle waves, wave particles, whatever that is. I mean, what is a particle wave? What is a wave particle? And so, yeah, we have a semantic problem because we didn't understand. See, they already move on to the theory. See, let me explain my theory to you. No, I don't want to hear your theory. I want to see the entity that mediates light. And they say it's a wave particle wave. It's a wave packet, What is that? Please draw it. That's the issue. And so, yeah, you have to start by illustrating the mediator of light. If you're going to say that light moves, hopefully only objects move. So if light is moving in any way, shape, or form, then it had better be an object. It had better have a mediator. So what mediator are we going to put? That's the issue. So that's what we're going to talk about today, the mediator, okay? And these people don't understand the question because they say, well, it's a photon, blah, 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 and then they move on. They want to explain their theory, not illustrate the objects. And it turns out that the same Nick Lucid, what he tells us is that it's just a bunch of probabilities, really. Huh? Yeah, light is just probabilities. Okay, so let's get it right. Okay, so here it is. Listen to him, not to me. Okay, hear from the horse's mouth. Here it goes. Okay, so we have all these probabilities. That's what you're looking at, probabilities, which is what, statistics? What's that got to do with physics? What's it got to do with the mediator of light? And they say, look, it's all these particles, and the ones that arrive are, depends on the statistical nature of the particle, whatever that means. I want to know how the universe works, and they're talking about statistic, which is some mathematical concept that has nothing to do with the question I'm asking. And so it turns out that, if you're going to simulate light with particles, we have some problems. And one of the problems that I raised was the laser ranging experiment, run by really the United States and the Soviet Union both ran that. And that's that they put a laser, for those who believe that we went to the moon. They put a laser ranging, an array of mirrors essentially, right? And they shoot a laser from the Earth, and that way they can tell how far the moon is, and it's getting closer, getting farther away, that kind of thing, right? And so the question is, they shine this laser at this tiny 20 by 50 centimeter, 20 by 50, right? Array. Okay, so tiny thing, right? So big, that's it. On the moon. And so they shine the laser at it. But imagine if you have to shine particles. You're throwing little balls now, right? So you're throwing little balls because that's what light is according to these people. But it turns out the moon moved. And it moves 1 kilometer per second. So when you're pointing your laser directly at the array, well, that can't be so, because it takes more than 1 second for light to reach the array and another second for it to come back. So it takes 2 seconds. It's a little more than 2 seconds, really, slightly more. So it goes and comes back, and it turns out when these people focus, it stays there. The light is fixed to the laser, to the array, to the lunar ranger, but the moon moved. So how come we can focus directly on there? That's the question. And so this is the question I raised, and so he tried to answer this, and he says, Bill, well, this is me. I said, lunar laser ranging doesn't work because you'd have to aim where the mirror will be. And it turns out he doesn't really put the question. He doesn't understand what the question is. So I have to put the question now one more time in red, in that red square. The question is that you can't explain this with particles. That's the issue. It's not that I'm falsifying the lunar ranging or all these nonsense that these people raise. No, you cannot explain lunar ranging with particles. That's the issue. That's the only issue. And she says, you do not need to pinpoint aiming at a tiny flat mirror. You illuminate the array. Yeah, but the array is only 20 by 50. He doesn't understand that. It's a very small array. And the issue here is that the array moved 1 kilometer away from where they focused. And you're talking about 2 kilometers by the time they received the light back here on Earth. So the array is not where you pointed to before you sent, the particles. So the issue here is that you cannot explain the lunar ranging experiment with particles, with discrete particles. Okay, by the time they arrive there, the moon is no longer there. That's the issue. And he doesn't understand that. So he raises issue, that you focus on the whole array. Yeah, you can't focus on the whole array because you're focusing on the array and it turns out the array is no longer there. Now it's over there, 1 kilometer away. So how do you focus? And that's not what happens. In fact, they do focus, meaning that light cannot be made of particles. That's how simple it is. Okay, you cannot focus. If you focus, which they do, then light cannot be made of particles. That's the issue. It would take 1 second for particles to reach there, another second to come to your eye. That's not what they see. They see instantaneously. That's how they see it there. And the only way, again, that you can do that is if every atom from the array is connected to every atom in the laser, or your eye, for that matter. Every atom's already connected. The moon can go anywhere it wants now because light will go along, the electromagnetic ropes, which we propose as mediators for light. Okay, so here I explained to him a little bit, saying that the retroreflector is 50 times 20 centimeters wide, right? And so in terms of the light going and coming and going, we have, the ranger is not there when you look at it. In fact, in terms of the size of the reflector, the fact that the moon moved, 1 kilometer is 2,000 times as long as the little array. So you cannot focus on the array like he's saying, because it ain't there anymore. That's the issue. It says the moon is 380,000 kilometers away. It takes photons traveling at 300,000 kilometers per second, a little over a second to reach the moon, let alone coming back, right? And this means that the discrete photons coming off the laser and traveling one way will reach the reflector's original location, but the reflector is now 1 kilometer away. In other words, the idiots at NASA would need to point the focus their laser where the reflector will be in 1 second. Okay, so they have to focus in advance to where the array is not. That's the issue, and that's not what they do. In fact, they focus directly on the array, meaning that if they can do that instantaneously, because as soon as they move the laser, right, and follow the array, it's because if it were particles, it would describe a curve in space. That's what would happen. That's not what's happening. What they see is directly. They see the array directly. Like I'm staring at you right now. If you move, and light if you're I don't know, 2 light seconds away, you're on the moon, right? And I want to look at you, right? Well, I got to look at where you will be, not where you are, because by the time the photons go and come back, you're not there anymore. You're over there. That's the issue. But he doesn't understand that. I think it's something straightforward. Okay, so how does he explain this stuff? Well, when they talk about light, they talk about geodesics. And so he says, light follows 0 geodesics of the space-time metric. Call it the road curves, if you like. Yeah, the issue here is that, he says, he's essentially saying that the discrete photons follow geodesics, which is like saying that you follow your run. Because geodesics is a trajectory. It's the motion of something. And so they're saying it's following the motion. It's like, when I run, I follow my jog, my run, the run that's in front of me. I'm following the run. That's what he's saying. And that's the kind of language these mathematicians use. And so, yeah, we have a problem. You don't follow your run. Okay, but that's what they're saying. And here's a little illustration of what they're talking about. They're talking about this, 2 elephants. And these 2 elephants are moving along geodesics. And they're going to bang their heads, wherever they meet. And this is what they call a geodesic. So the geodesic, what is it? It's a trajectory. It's an itinerary of the 2 elephants. So if you have the Earth there, you have the 2 elephants. And they're going to run along and follow, as they say, the geodesics. Why would they follow the geodesics? And they say, well, they do. I mean, why can't these 2 elephants go in parallel, completely in parallel, and not curve around? And again, we don't have an answer. They just say, it is so. So they have no explanations for these types of phenomena. They just say, it is so. We measured it. Okay, tell me why. What's the cause? And so when you raise issues like that, they say, oh, Bill, you're doing semantics. So I say, gravitational lensing bends light. Are the idiots of math bending the road or the car? Because, when they say they bend light, we're talking about the mediator of light and not the fact that light is following a curved road, following the geodesic, right? So is light following a curved road, or is light deflecting from its rectilinear itinerary? Which is it? And so you say, oh, you're doing semantics because physics is measured. No, you got to explain after you measure, and they don't explain. They just say it is so. And again, measuring is what these idiots do. In science, we do what he calls semantics. So that's the difference between science and what these people do. So we have a problem with their language, very important, and we still don't understand what the mediator of light is according to their version. We want to see what their version is, and please explain whatever phenomena with your version. I don't care if you propose particles or waves or wave packets. Propose whatever you want. But then explain with that thing that you proposed. But see, they switch around. They say, well, here I use the particle, and over there I'm going to use the wave. And sometimes I use the wave packet, what, it's like, what is light? Is it a wave or is it a particle? And if it's a wave, what are you talking about? If it's a particle, what are you talking about? Are you talking about what is a particle? A vibration of a field, a local vibration of a field. And that means that, again, we're talking about numbers. So we're talking vibration of numbers here. In the case of wave, it's also vibration of numbers because it's made of two fields, which are made out of vectors. So we're talking about just vibrations of numbers. Is that what light is? A probabilistic thing related to vibrations of numbers? I mean, what are we understanding with all this? And here we have good old Lucid, again, Nick Lucid, and he's going to tell us something about the fact that, light travels at different speeds in different media. And I guess, again, he's going to do this with particles, waves, I don't know. Let's see which one he uses. And here he goes. Listen to him. So light slows down, perhaps, maybe, because we don't know that. According to him, we don't know that. Second, where he's, I guess, illustrating a one-way mechanisms, meaning what's he doing? He's either using the wave or the particle. So whichever one we use, he's saying it slows down inside a more dense medium. But he doesn't explain why. Why does it slow down? He says it just does. It's a statistical issue. And here he explains a little more. I hope you understand it. I don't. So here goes. Listen to him, okay? So we have now many paths for light, and I guess they take an average, a probability, a statistical issue, and that's how they explain it. Explain with quotation. They haven't explained anything. What they're saying is, look, mathematically, that's what we get. It's a probability issue. In fact, they invoke Fermat's principle, French guy who came up with the least time for the trajectory of light. And here, listen to him. Again, this is Nick Lucid presenting Fermat's principle. Okay, listen to him. So what is it? We have probabilities on top of probabilities on top of probabilities. It's all probability. It's probable. Maybe. Perhaps. That's his side. Here we have another fellow, another bozo. He's from Fermilab. The name is Don Lincoln. He's going to tell you a different story, okay? He's going to tell you, he's got the right answer for white light curves. And it might have something to do with the speed of light, the fact that it changes speed from medium to medium, but he's going to give you a little more. He's going to tell you exactly why, light goes slower. Okay, listen to him. Here goes.
we can see what light does when it enters glass or water or any transparent medium. It bends. And the reason that it bends is because the epsilon in glass is bigger than in air. You start out with glass with no electric field in it. The glass has charges in it, but they're arranged in a random way. But when you send light in, you impose an electric field on it. That field makes the charges move around, which sets up a counterbalancing electric field from the charges. The result is that the electric field in the glass is lower than it is in air because of how the electric field from the glass is in the opposite direction. And this is the reason that the perpendicular electric field is lower in glass. And that, my friends, is why light bends when it goes from air to glass.
So now you know, okay? That's why light is slower in glass. It's got to do with all these fields. He explained it. What is a field? A bunch of numbers. I mean, look it up. Don't take my word for it. It's a value at each point in space. So he's saying because of all these values, light comes out slower. What are we going to say? So again, all these people are just talking about numbers. They don't explain anything. It's just a description based on mathematical abstractions, which they have converted into physical objects. You can't use the word field, the word wave, because they're not to explain or simulate light because they're not physical objects. They're just a bunch of numbers. You can't use the word energy, a bunch of numbers. They're all numbers. So these are not explanations, and of course they don't. I guess that's why Richard Feynman said, we have no clue. We have abandoned the attempt to try to explain how the universe works. And yeah, they never will. And the only issue is they gotta let go of the particle hypothesis. There are no such things as discrete particles because you cannot explain a single phenomenon of nature, invisible, the invisible, intangible part, the mediators. You cannot explain them with particles, with discrete particles. Everything had better be connected in the universe. Otherwise, you cannot explain. Otherwise, you got to introduce action at a distance, entanglement, gluons, that stretch somehow. Action at a distance, which is black magic. So the entire universe is physically connected somehow. Okay, you can't do it the quantum way. What does quantum mean? Discrete quantity. And again, we're not talking about quantities, which is what math is all about, which is what quantum was all about from the start. So they try to do it mathematically, and that's where it all failed. Okay, now another question is, why does light, when it exits the glass, okay, this guy says it's the field that, electric field, it's modified so it goes slower outwards. Great, let's concede that. Why does it go faster again? Why does light go faster again once it goes back to the original medium? You have a little bit of glass in the middle of space, right? In space, they all agree light travels at 300,000 kilometers per second. No problem. Okay, it goes through the glass, right? Glass is, we used 1.45. Most people use 1.5. It doesn't matter. 1.5 times is the refractive index. That means you would have to divide the speed of light by 1.5 and you would get your 200,000 kilometers per second, which is what it travels allegedly, according to these people, through the glass. But now it goes to the other side of the glass. So it should go back to 300,000, I hope, right? Because now we're back into space, right? And so the question is, why, after slowing down through the glass, now it picks up speed instantaneously? As soon as it passes that last barrier of atoms of the glass, of the molecules of the glass, suddenly it goes back to 300,000. Cranks up the speed, goes back to 300,000. How does it do it? What's the mechanism? And so they don't have a mechanism, but so here's this bozo from the circus, right? And he says the following. Says, speeding back up is simply the wave obeying the vacuum dispersion relation, blah, 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 right? Once it exits the medium. Again, it's a description. These people don't even understand the question. What do you mean the vacuum dispersion relation? He's talking about math. He's saying we describe it and it turns out that, it goes back to 300,000. That's all he said. He's not giving you a why, a physical cause. Okay, he just said the vacuum dispersion relation. Great. And but he uses the wave. And so is this what he's using? Because he says the wave obeying, right? And so the wave is that thingy that you see there, looks like a bunch of arrows, but it turns out, you're staring at numbers being represented by arrows. All those are numbers, vectors, fields, the wave, all that you're staring at are numbers. And so they're not talking about some physical entity. They're just saying, look, we've measured and this is what we came up with. Okay? And so, we have a problem because they have a semantic problem. And second, they don't understand the question. They don't understand the question they have to answer. How will they ever discover what we're looking for if they don't even understand the question? They keep giving you answers that have nothing to do with the question you ask. I want to know what physical entity underlies light. Whatever you use, I don't care, whatever you use with that explain light. So whatever you introduce, right? You introduce particles, no problem. Now explain light. And then they say, well, we measured. I don't care if you measured and that you have the equation. We don't give a damn about that. Okay? This is the issue. Okay, so, the speed of light is 300,000 kilometers per second. It's a constant, right? According to the equation, C equals frequency times wavelength. That means when frequency goes up, wavelength must go down and vice versa in order for little c to remain a constant. Okay, I don't know if I need to explain that again. You have little c, 300,000 kilometers per second, equal to frequency times wavelength. Means frequency and wavelength are inversely proportional. If frequency goes up, wavelength must go down for c to remain constant, and vice versa. When wavelength goes up, frequency must go down for little c to remain constant. And the question, here's the million-dollar question. Why don't we raise both the frequency and the wavelength so they're both higher, and we travel at not only faster than light, we can travel at infinite speeds, at any speed you want, because we raise both the frequency and the wavelength. And so here's his answer to this question. He says, frequency and wavelength are tied by the dispersion relation. Again, he talks about relation, like saying that's what holds these two parameters, these two variables, that's what holds them constant or at a certain level, because they're governed by the dispersion relation. He thinks he's answered the question. I want to know physically what's happening. Why? Why can I not raise both the frequency and the wavelength of a wave, right? Because that's what we're talking about if we're talking about waves, right? Why can't I increase both of them? If we're talking about particles, whichever way you can imagine frequency and wavelength in terms of particles, well, why can't I put more particles or spread them out or whatever and make light go faster? That's the only issue. And then he comes up with this other nonsense. Group and phase velocities can exceed c in dispersive media without information transfer. Well, I don't know what science doesn't deal with the word information. Okay, it's garbage that mathematicians introduced there. We don't use the word information because information is an abstract concept. We don't use it in physics. We have no use for information. And we can't transfer concepts, so we don't transfer information. Any idiot who uses that language should be kicked out of science. Okay, that's the first thing. The other one is, group and phase velocities. Okay, they can exceed little c, no problem. Can we increase your group and phase velocities billions of times both, so that again the speed of light in dispersive media or whatever within the wave or whatever you want to propose, can we make light travel billions and trillions of times faster than light? That's the only issue. So don't tell me it can go a little faster in a phase velocity or whatever. Tell me if they can travel at gazillions of times the speed of light. Because if we can raise the frequency and the wavelength, right, gazillions of times, then we should be able to travel instantaneously anywhere in the universe. Why can't we do that? What's preventing us from doing that physically? That's the question. Again, we got to go back to the entity. What mediator does light have? What is the physical mediator of light? And hopefully if something is moving, it had better have a mediator. And so this is the issue. Okay, we have another issue with light because, when you shine light, like through a lens and to a mirror, it turns out that the mirror sends the light right back to the lens and back to your source instantaneously. Why? Because it's retracing its exact path. Let me repeat that. Light retraces its exact path. When it goes, it also comes along the same line. How can you do that with particles? The moon, right? You send particles to the moon, but the moon's no longer there. So if it's going to hit the mirror, it better, describe a curve in space, and then another curve to come back to you, right? And, here you have a little flashlight or whatever, you point it at the lens, and from there to a mirror, why do you get the reflection right back instantaneously? I mean, everything in the universe moved. We moved with respect to Jupiter, the Earth moves around the sun, etc., etc. And it turns out that light always retraces its exact path. How do you do that with particles? How do you do it with any one-way mechanism that you propose? Any one-way, well, yeah, it's a mechanism, but I mean, we're talking about what the mediator of light is. Can you do it with particles? Can you do it with waves? Or one way? By the time they go, will they retrace the same path that they went? How do you do that? How do you explain that with particles or waves? And so this is the issue, and they don't understand the question. And here's his answer to that question. He says, Maxwell's equations are time reversally symmetric. Yeah, we know this. Don't. Is there an echo in here? We know that's the question. Why is it symmetric? He said, Lorentz reciprocity theorem guarantees ray reversibility. That's his answer. Okay, so we get a mathematical answer. Oh, we proved it. Yeah, tell me about it. That wasn't the question. The question is, can you explain it? And of course he can't, because for that you would need to know what the mediator of light is. And if you do it with particles, you cannot explain it. And if you do it with waves, you cannot explain it. So you have to get rid of the wave and particle hypothesis. Waves first, because they're not physical objects. Particles, because they're not talking about particles. They're talking about numbers. And so with numbers, yeah, we can describe it mathematically, but explain it physically, I don't think so, right? And if you have the particles, yeah, this is what you would see through space. Imagine an atom within the sun, okay? That atom is pumping, right? It's you got this quantum jump, right? So the atom is going from energy level to energy level, back and forth, right? In different places around the nucleus, right? One atom, right? And that's when it's creating light. It creates light when it jumps from one energy level to another. That's the official version, okay? But this atom is spinning. The sun is spinning at great speeds and sending all these photons that come out of the sun outwards. So this is what the sun would be describing, like a sprinkler system, right? Nothing would travel straight. Everything would travel in curves around, to your eyes. And that's not what we see. We see direct light, coming to us. It's not curving at all. The photons are not flowing all around space like a water sprinkler. And so, yeah, we have a problem with their version with particles. You can't do this. You can't simulate light with particles. That's the question. That's the issue. Okay, then we had the issue of why light goes through walls. And so this is what he answers. And it says, X-rays pass through walls. Well, it says, I say that. X-rays pass through walls. Why not visible light? He says, refractive index comes from electronic hand structure and resonances. Yeah, refractive index is a mathematical concept. That's not an explanation. It's just a description. Visible light is strongly absorbed, scattered. Yeah, tell me about it. X-rays couple weakly and have longer attenuation lengths. All these answers, coefficients and constants explain why. Explain, he says, huh? Coefficients and constants explain which wavelengths penetrate which materials. So again, he thinks he's explained when he's only giving us mathematical descriptions. He doesn't understand the question. He really doesn't understand the question. And all they do, all these folks, right, all these clowns, what they do is they simply regurgitate what the establishment fed them. Whether in school, high school, college, they just regurgitate the same thing and pass it on. No, you have to explain. And what the mathematicians cannot do is explain. We have the wrong people doing explanations, and that's what people want to understand out there. People say, please explain. I want an explanation of gravity. I want an explanation of light, of the atom, and they do not explain. They give you a description, a mathematical description, which they turn into an explanation. Say, there, I explained it. I didn't understand anything. Well, you got to take math to understand it. Why do I have to take math to understand why, for example, pencil falls to the floor. Here's a pencil, gravity. Why do I need to take math to understand the mechanism of what's causing that? And this is the issue. These people don't understand the question. So they're not answering the question they're supposed to answer. One. Second, they tell you they can't answer. Those people who just figured it out, they say, well, we can't answer. These people are telling you, oh, yeah, we can explain it. Oh, you can? Yeah. Here's the numbers. Here's the experiment. Here's the observation. Here's the verification, the falsification, all that nonsense that they come up with. Okay, he challenges the rope, and he says, the rope hypothesis makes no quantitative predictions. Absolutely. Thank you. Yeah. So please don't request them. Okay. We don't do astrology, palm reading, witchcraft, none of those things. Okay. We don't do black magic here. We don't do predictions. Okay. Predictions belong to religion or to astrology or whatever. No, what we do, we explain. Okay. That's what science is about. That's what physics is about. Explanations and only explanations. Nothing related to math has anything to do with physics. You can do your math and describe all you want over there. When you come to the physics class, come to the physics conference, we want an explanation, a physical interpretation of how you think the universe runs. For that, you need to figure out what the invisible, intangible mediators are for light and for gravity. Otherwise, you can't explain it. Can we go to the lab and verify, falsify, blah, blah, blah? No, you can't. You're talking about invisible, intangible. Invisible, intangible, invisible, intangible mediators. What is lab? See, touch. That's what a lab is, see, touch. And we're saying it's invisible and intangible. I mean, here's the pencil again. Do you see anything here? Can you touch anything here other than the air, right? No, of course not. I'm running my hand right through the objects that either are pushing or pulling on this pencil. It's really pulling, but assuming you have a different theory, no problem. But then you have to identify the objects, and hopefully they're invisible and intangible. Don't tell me we're going to go to the lab to find out, what's pushing this. No, this is not an issue of going to the lab or verifying or falsifying. This is an issue of please explain what's causing this to fall to the ground. And for that, I need no math. I need whatever object you propose had better be invisible and tangible. Otherwise, you're not imitating what Mother Nature has out there, because what she has out there is invisible and tangible. So don't ask me to go to the lab. Don't tell me, let's do an observation, let's do a verification, let's do a falsification. No. The only way you're going to falsify is declaring that this is an irrational explanation. Then you can falsify it, meaning you convince someone. Otherwise, you just need to explain what's pushing or pulling on this pencil. That's it. There's no other possibility. And it better be, whatever you propose, better be invisible and intangible. And here's my version of what the rope does. We explain. That's what the rope version is all about. The rope hypothesis makes no quantitative prediction. Absolutely. We don't make predictions. If we are to talk about how the electromagnetic rope relates to quantities, the electromagnetic rope explains these numbers. No, we're going to explain the numbers, right? Not the mechanism. We just want to explain the numbers. Why light is so fast? Light travels at 300,000 kilometers per second. Why is it so fast? Well, the rope can explain that because torsion, a torsion wave, a 3D torsion wave, right? If we want to call a torsion a wave, is the fastest thing imaginable. There's nothing faster than a torsion. Nothing. Because it's already connected at the other side of the universe. That's why. So you don't have to travel to the other side of the universe to find out. Torsion is the fastest thing that anyone can imagine. Okay? And I always suggest people put a rope between two walls or between two things hanging onto them, make it very tight, and put two clothespins at each end. As soon as you move one clothespin, the other one moves instantaneously. Why? Because it's already connected at the other end. That's why. Rope is already extended. Okay, and it's invisible, intangible. You can pass your hand right through it because that's what you have to propose. Whatever you propose has to be invisible and intangible. Otherwise, you're not imitating Mother Nature. Then the speed of light is constant. Why? Well, the rope obviously can explain that very easily. If you increase the frequency, meaning the number of links, each link has to be smaller. And if the links are longer, then you have fewer links. Very simple, and that's the difference, and that's what the frequency and wavelength stand for in that equation. That is the equation of a rope. There's no other thing that can imitate that equation. Maxwell came up with that equation, by the way. The speed of light is independent of the movement of the waves of the source. Why? Because the atoms simply glide through the rope, and as they do, the rope feeds into the atom because the rope, each thread makes up the atom itself. So it's not like it's connected separately. The ropes become the atom. Okay, each one thread goes through the center and the other one goes around it. So you're gliding through the rope, and because of that, you're not increasing or decreasing the frequency of the rope itself. Okay, so that's the only thing that can more or less that circumstance, that situation is what explains why the speed of light is not added to the speed of the source. Okay, any atom falls to Earth with the same acceleration from a given distance. At a given distance, you have all these ropes from the Earth, right? This is gravity, right? Converging upon that atom. So it doesn't matter what the atom belongs to, what entity could belong to an astronaut, to a feather, or to an elephant. It won't matter. If it's a hydrogen atom at a given distance, you have the same number of ropes from the Earth converging upon that atom at a given distance. Period. That's what it is. That's what weight. Weight is location dependent, location specific. Okay? It's a static concept. Weight, as soon as you move a teensy-weensy inch, or even less, a centimeter, a millimeter, whatever you move, you've already changed your weight. Why? Because suddenly the number of ropes, independent ropes that are tugging you from the Earth has changed. That's what it is. And so, weight, these people don't understand. They say that weight, it changes with time. It changes with for example, if the Earth, if the sun were to disappear, the Earth would take 8 minutes to learn about it. No, if the sun were to disappear, there would be no ropes from the sun to the Earth. If we could make that magic trick and make the sun disappear, the Earth would fly away instantaneously because it's being tugged by the sun. No sun, no tug, instantly. It's like you're hanging from the mountain from a rope. I cut the rope. It doesn't take 1 second for you to receive the message, the information. No, you fall instantaneously, okay, because that's what was holding you. The tug on that rope. Okay, it explains the underlying cause of the principle of equivalence. That's a long story, but essentially we're saying that Newton's equation is equal to, a gravitational equation is equal to his second law, force equals mass times acceleration. Okay, so we have an explanation for all these numerical, these mathematical concepts. Okay, we're not interested in answering that. We're just saying we have no quarrel with the equations. Okay, we have no quarrel with the equation. We're just giving a physical interpretation to these equations, and we have, I guess, a physical interpretation for them that doesn't rely on particles or waves. What we need to get rid of, what we need to kill finally is the wave and the particle proposals. That's what dies. Okay, meaning all of quantum dies and all of general relativity, because relativity is based on the particle nature of light and the wave nature of light. They're talking about waves, gravitational waves, light waves curving around the sun, etc. So they're simulating everything with waves and with particles also. So both theories die a sudden death, and together with string theory, which is trying to merge the two. Okay, so yeah, we have a problem with the particle hypothesis essentially, and the wave also irrelevant. In fact, they don't use the wave as often enough. They usually use the particle. And what is a wave made of? Probably particles, right? Okay, and finally he says, Bill attempts to falsify observations. No, we're not forgers. Yeah, we don't try to falsify anything in science. It's the irrational mind that talks about observations and about falsifying. In science, we do not falsify anything. Scientists are neither forgers nor counterfeiters. It is the mathematicians who spend their time falsifying theories to match their equations and selling their irrational theories as fact to the general public. One thing we don't do is talk about facts, proof, evidence, knowledge, experiments. No experiment's going to tell us the nature of light because it's invisible and intangible. So whatever you do had better be invisible and intangible. So don't ask me to go to the lab to run some experiment and obtain some evidence to present at the conference to be falsified by some other nut in there, right? No, it doesn't work that way. This is what they call armchair physics, which is the real, true, genuine physics. You sit back, you get a beer, and you visualize. You try to imagine how Mother Nature runs this universe. And we're not going to do it by going to the lab and saying, I'm going to run an experiment. What are you going to run an experiment for? What are you trying to see? Are you trying to see the invisible? Are you trying to touch the untouchable? I mean, what are these people trying to do? This is so incredible. Here we are, so many centuries later, and these people are still doing experiments. What for? Science needs to know how we run this universe. That's all science is about. And that's all it ever was, but they never figured it out because they never defined science or physics. They have these irrational definitions of the word science, of the word physics, and that's why we ended up in the big mess that we have today. Okay, we had this other fellow. He's an ether. He belongs to a different circus. He belongs to the ether circus. Circus ether, okay? And again, we start with the same question for him, right? This clown, we try to make him understand what the question is. The question is, what is the mediator of light? And I guess he's going to propose ether vortices of some kind, you know? Okay, I don't know how he plans to simulate light. I didn't read his paper because when I went to his paper, he said he had a picture of the ether. That's what I was interested in. First, I need to see what this ether thingy is, this thing that nobody ever seen, nobody can draw, nobody can illustrate. And I said, yeah, that's where I start. Show me the ether. And so he gave me the runaround for a couple of weeks, probably more, and finally sent me to the ether. But the first thing he said in one of his comments, he said, atom is translucent. In translucent objects are spaced farther apart than in opaque materials. He's going to explain why, light can pass through. But I'm saying light pass through. What do you mean light pass through? Are you treating light as particles? Are you saying, or waves? Are you saying that this thing goes one way and it's passing through? And again, we have a problem because, again, I didn't read his paper, but I need to know what this ether is, which is the mediator of light in his case. So how does he reconcile the mediator that he's talking about, the ether, and talking about light passing through objects? I have a problem. First I need to see the ether. Then I can visualize what he's talking about when he says light pass through. And so, again, I don't know what he's talking about until he can illustrate the ether. And so, again, we went around for a couple of weeks. He finally sent me to a page of his, page 8, I think it was. And he says, when I say ether, people can at least relate to general idea that there's something present between objects. Yeah, something present. What are you talking about? I mean, are you talking about a rope? And as soon as I say rope, no, that's not it. Okay, so what is the something that is between two objects, two atoms or two particles, two whatevers? And so, again, until I see this ether thingy, I don't know what he's talking about. And he says the ether is a real physical medium. Good, great. That means that we can illustrate it, because if it's a medium, why can't you illustrate it, right? And so he says it explains interaction, blah, blah, blah. It explains everything. Once Yeah, once you have the physical object, maybe you can explain stuff, but until we can see the object, we cannot explain a single thing. We cannot visualize the physical interpretation that you're offering. We need pictures, images. First show the mechanism, then you can explain it. But first, I ask you to explain how a motor works. And you say, well, I don't have a motor. I don't know what a motor looks like or never seen a motor, but let me tell you my theory. No, I want to see the motor first. Don't talk about a motor and how it works and you don't show me the motor. You don't show me even the pistons or whatever. Come on. First thing you got to do is show the objects. That's the first step. You don't have objects, you can't begin your presentation, period. That's where it dies. And that's why I didn't even read his paper. I mean, until I see the ether, I've got nothing to even imagine. I don't know what he's talking about. So he went in there after several weeks, and he told me that it's sent me to page 8, I think it was, and he says, oh yeah, there it is, page 8. He says, there's the ether. And in the page 1, he had another similar thing, which I think is also the ether. But there's a little bit of difference between them, and you can see that one has something around it. The other one just has the frame of, it's like he cut it off there, right, the first one. So I don't know what's giving shape to that first ether that he's illustrating there. And it turns out that it looked to me like it was swirled molasses. And just by sheer coincidence, I just went in there and said, well, I'm going to put in images in Google, swirled molasses, see what I get. And I got the pictures that I wanted. And the one on the left there, at the bottom left, that's the original one. I changed the colors, put opposite colors, and it matches exactly what he's putting in there. So no longer is it called the ether. Now it's going to be called swirled molasses, okay, folks? From now on, please don't insult them by saying the ether. It's swirled molasses. And yeah, the only issue I've got is, what is this? What are those things that are giving shape to the to molasses? In the case of the one at the bottom, it's in a cup of some sort, and that we can all understand because it's got something that holds it in. And the question on the one on the top, what is that grayish thing that encapsulates the bluish swirl there? That's the question that I've got. And so he's got to identify that. He can't say, well, the one on the left, the one on page 8, that's the ether. Yeah, I need to know what's outside of that, what gives shape to that. And again, if he's got that swirl, that means that, the ether is made out of gazillions of particles to make that swirl. It's got some kind of fluid or gas or water or whatever, right? But the problem there is that he says it's made out of a single piece. It's continuous. So we got a problem with continuous, meaning single piece, and made of pieces. Those are contradictory descriptions of what he's trying to tell us. And so again, until I see this ether and find out what it is and what's outside of it, what gives it shape, we don't have something to start with. There's no reason to read his paper. What are you going to read? Nonsense? So he kept for several weeks saying, I've never seen the air. So I've never seen the ether, and you want me to imagine, but I see no reason to. He sees no reason to imagine his ether. He's just going to talk about the ether, whatever it is. You're going to talk about the motor without the motor, in other words, right? So electricity, magnetism, and gravity are invisible. Yeah, tell me about it. But nonetheless, very real phenomena. Yeah, he said nothing there. I have never seen the air. He's never seen the air. One of those few people on Earth that hasn't seen the air. So I had to show him what the air looks like. So here's the air, okay? There you have air, okay? You can see air. I've put it in a little, in the Universal movie in a single frame, so not a single atom, not a single electron is moving in there, because that's what a single frame in the Universal movie represents. And so there you can see air. That's what air looks like. It's just a blob of air that an astronaut, just let go from a balloon. And as soon as it comes out of the balloon, it's going to disperse, right? But before it disperses, I took a picture of it. And there we have a snapshot with God's camera. Nothing is moving. Not a single electron in there is moving in that frame. Everything in the universe is frozen still. And there you see what air looks like. This is green air, by the way. But that's what it would look like. A bunch of atoms, right? A bunch of molecules forming some kind of blob. Does it have shape? Hopefully it does. What is the shape? We don't care. That's not the question. The question, does it have shape? And I think that thing has shape. Okay, so shape all by itself. It doesn't require any other thing except, an enclosure, something on the outside of it. But other than that, there you have it. That's what we want them to do with his ether. Show me your ether and something around it. Identify what's on the outside. Very simple. Otherwise, these clowns, they got to go back to the circus. Do some more work. Erase their boards. I don't know. Okay, then he said, density is a forbidden work in physics? Are you kidding me, Bill? Density, like in density of water droplets, is a real physical phenomenon. Again, he says it's a phenomenon. Yeah, density is not a physical object, okay? And but that's how they treat it. It says it may not be an object, but it still is a real phenomenon and very important in physics. No, absolutely not. Density is a mathematical word, and there you see the definition. If you looked it up, you wouldn't have said something clownish like that. Density is a measure of how much stuff is. Much sounds like math. Much. Where did I hear the word much? I think in math, right? Yeah, measure of how much stuff. That's what density is. Packed in a given amount of space, right? So there you see the equation. Density equal mass divided by volume. I don't know if there's a physical object called mass. I don't know if there's a physical object called volume. I think those are just numbers. You have kilograms, some volume there, right? And they dilute and you got density. That's it. And when you have a black hole, you have zero density. And this zero density thingy, affects stars far away. So that's great for mathematical physics, right? But this fellow doesn't believe in black holes, but he's using the word density again. And yeah, we don't use the word density in physics. Okay, so you're outside of science. You're talking math. Okay, that's got nothing to do with physics. What is physics? Rational explanations. You cannot explain anything with the word density. Okay, density only has to do with math. Math does not explain. Math only describes. Period. We're done. No more. Okay. Explain. You need objects. We're talking about physical interpretation. You need to put an object in. I need to see the motor. And once you have the motor, I don't need any math. Just tell me how it moves and why it moves the way it does. Don't give me, well, we have so much energy coming in and the field vibrates over here and there's so much mass. Forget about all that. We need density, right? We need to see the physical objects in motion. That's what we're asking. We're asking you, please explain the mechanism of gravity. I'm not saying how fast it moves. I don't care about that. We don't care about quantities. We want to know what the mechanism is. Why does a pencil fall to the floor, not to the sky? What's causing that? How can we get those questions answered? These people don't talk. They say, what's the density? No, density has nothing to do with the question we're asking. We want the mechanisms, not the density. Density is a mathematical word, has no place in physics, no place in science. Science is not about description. Science is explanations, rational explanations. So he says, according to bgaede, you don't need experiments in science. Absolutely. I don't need an experiment to find out what physical object mediates gravity, what physical object mediates light, etc., or what an atom looks like. I don't need any experiment or any math for that. Okay, so I don't need what experiment are you going to run? Here's the experiment. Okay, once again, okay, we let go of the pencil. Okay, falls to the ground. So I did the experiment. Let me do it twice because they say it's got to be repeatable, otherwise it's not scientific. Okay, so let's do it twice. 2 times now. Okay, no problem. Okay, so I did the experiment. What did I learn? Did I learn what the mechanism of gravity is? Why it's pulling the pencil downwards or pushing the pencil downwards if it's a push force? For that, you need to identify the physical objects that are pushing or pulling. Don't talk about volume. Don't talk about pressure. Don't talk about density. None of those words have anything to do with the question. The question is, what causes it? I need to identify the objects. You need to make the objects visible so that we can see your mind, what you have going through your mind. That's the issue. Okay? He says, just invent the theory, imagine it in your head, and that's enough. Exactly. That's what a theory is. You present a theory, you say, look, I think this is how Mother Nature runs her shop, or Father Universe runs his world, right? That's it. No proof. You can't prove light. You cannot prove the mediator of light. You cannot prove the mediator of gravity because it's intangible and invisible. What are we going to do? Go to the lab to touch gravity, or the mediator of gravity? Are we going to go to the lab to touch the mediator of light? See it? Of course not. This is something you can only visualize, and you have to make sense of it. So you put a mediator and say, with this mediator, let me make sense of light. Let me make sense of gravity. Let me make sense of the workings of the atom. Then, yes. But, it's not a question. You can invent angels if you want, but then you got to reconcile the angel with, with the what you're explaining. And this is where you run into trouble, because you have to show the consistency of the angel without introducing too many variables in there, right? Because otherwise, you get into Occam's rule. Anyways, and again, that's got to do with belief. Some people want to believe in angels. You can't stop them. They think that angels move the earth around the sun. What are you going to do? That's what they believe. Okay, you have people believing the flat earth, others believing we didn't go to the moon, and you have all kinds of people out there. And everybody believes in whatever they want. No problem. I'm not going to twist your arm and make you believe in angels or in God because that's what I believe in, or vice versa. Don't try to convince me of your religion. I just explain so that you understand. That's what we're talking about. And so science is what? Rational explanation. That's the definition of science. That's a scientific definition of the word science. Okay? And so test and experiment, what do? They give you evidence. What is evidence used for? To persuade you, to convince you. That's why we use evidence. So that's why it's not part of science. It's part of religion. Evidence is part of religion. And proof knowledge, again, part of religion. Knowledge or proof means I convince you. I persuaded you and was able to convince you. That's all that, another person was unconvinced by the evidence, still is skeptical of your theory, okay? And so he accuses me, he says that what I do is not modern physics, modern science. He says, well, what you're doing is not modern physics. He says, today physics is an academic and professional field, is about building mathematical models that match observations and can be used for predictions and technology. Yeah, that's what these people do. That doesn't mean that what they do is physics. We have to define the word physics, then find out if it matches what they are saying that they do. And he's saying, but that's what they do. We have to match the word physics to what they do and not define physics rationally and force the mathematicians to follow the definition. So we have a problem. Yeah, we have a problem because if something is broken, you got to fix it. And he's saying, don't fix it. Let's keep using it as is. The chair has one broken leg and, we're sitting down and falling sideways. Don't fix it because we all sat on that chair and we all have to deal with it. No, let's fix the chair. If it's broken, let's fix it. And they don't want to fix it. They say there's too many people out there that believe in the broken chair and we just have to live with it. And no, I don't agree with that. I rather fight the whole establishment. I don't care if I'm all by myself in the world. Or like Curly said once in Three Stooges, they said, all for one and one for all. And Curly says, I'm for myself. I'm for myself, okay? Anyways, what you are doing belongs to the tradition of natural philosophy. I have no idea what that is. Philosophy, nobody defined the word in 1,000 years, in almost 3,000 years, for certain 2,500 years since Plato, right? So nobody defined the word philosophy. Today, nobody knows what the word philosophy means. Stanford Encyclopedia of Philosophy, they haven't defined the word philosophy, so you won't find it in their dictionary. And you're saying, hold it, these are the number one site of philosophy in the world, and they don't have a definition for the word philosophy. What is philosophy? Love of wisdom. What's your degree in? Oh, I got a PhD in love of wisdom. Oh, great. Okay, so he said, you will always be in a semantic fight with people who are using the current accepted definition. The current accepted definitions, they don't exist. That's the issue. And they're all irrational, just like the word philosophy and the word science and the word physics. They're all irrational definitions. And if you deal with irrational definitions, you're not going to communicate your theory, and that's where we are at today. Nobody can explain anything about the universe of the invisible, intangible mediators. Why? Because they haven't defined the words. They don't know what an object is. They don't know what a thing is. They don't know what exist means. They don't know what a location is. They don't know what motion is. They say it's the change of blah, 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 blah. Change is already motion. So don't define motion in terms of change. And so on. I mean, it's on and on and on. All definitions of mathematical physics, you can call it physics, are irrational, are garbage. They should all be thrown in the trash can. And that's why, definitions are important. You cannot make your case without definitions. And he says, no, you should follow their definitions. Yeah, I guess. But this is the problem today. All these people, they don't believe that you have to modify the language. And they say, no, let's keep using the same language we've used all these years and see if we can make sense of the universe with all these irrational definitions. That's what they're saying. And the answer is no. Okay, let's move on to the subject matter of today. This bozo also criticized my notion of stopped light, the fact that they claim to have stopped light. And yeah, you can see why he's a clown, because, again, these people don't understand. They just don't understand physics. They say, look, they ran an experiment, they proved that light could be stopped, and blah, 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 blah. We have evidence, it's been falsified or verified or whatever. They talk about nonsense. They talk about experiments and proof and evidence. They don't talk about mechanisms. And that's why they never understand the question. And when I come around with a question, they say, what are you talking about, Bill? You lost me. Yeah. And so here, let's present the question as I presented the other day, and this is what he answers. Claims that light cannot slow or stop. And so we need to put it in the proper context, okay? The irrational mathematical version is that the mediator of light consists of one-way mathematical waves or magical particles. That's the official version, okay? We're talking about quantum particles, mathematical objects, as they call them, right? In other words, they don't act like what they call classical objects, meaning rationally. They can be, two particles can be at the same place at the same time, which is not true for what they call classical particles. That's the issue. So they have all these weird Alice in Wonderland properties, and they call them quantum particles or mathematical objects, and they try to get away with murder because what they're introducing is irrational concepts. That's what it is. That is what the rope model challenges, the mediator used to explain the properties of light. Little c is a constant, right? C equals frequency times wavelength, right? Constant means that c does not change value, but that when frequency goes up, wavelength goes down. That's what the little c stands for. You can't change little c. These people try to do that at all times. And so we have light traveling at this speed. If you want to change that, little c and put 0 there, which would be a constant, which would mean that light is not moving at all, well, either lambda or frequency have to be 0. One of the two has to be 0, or maybe both. But at least one of them has to be 0. Otherwise, you can't get c to go down to 0. Okay, so keep that in mind. Light on the red end of the spectrum is invisible, not because it's slowed down, but because length is longer. So we are beyond the range of what they call wavelength, meaning length of a rope, right? And there are fewer links per unit length. That's what the equation stands for. That is the equation of a rope. If we manage to freeze atoms in a region so that the electron membranes do not expand and contract, meaning quantum jump, right? The electromagnetic ropes between those atoms will not torque. That's what it is. You don't have any torsion. So if you can freeze the atoms and they don't pump, they don't expand and contract, you've frozen quantum jump, right? Then the rope has no chance of torquing. Light has stopped. Not because one-way photon balls have been frozen in midair. Light has stopped in the sense that the atom is not pumping torsions to your eye. Okay? So let's see if we can understand what all that means. Okay, we're saying that we have this little equation called the speed of light, little c, it's a constant, it's equal to frequency times wavelength. And here you have frequency times wavelength. Okay, there it is in a rope. Okay, the number of links, frequency. How long each link is, wavelength. Okay, and when one goes up, the other one goes down. Here we have more frequency, more links, and each link is shorter. And here you have, the opposite. We have the links are longer and we have fewer links. That is the equation of a rope. Maxwell's equation is not an equation of a wave or a particles, series of particles. It's a wave. It's an equation of a rope. The rope is the only physical object that can simulate Maxwell's equation. So those notions that people have that we left classical physics behind because we could not explain anything, it's because you simulated everything with particles and waves. That's why you could not explain anything in quantum mechanics. Period. That's the only issue. Okay? Why can't you explain? Because you never defined what an object is, and you're using concepts as objects, you're using fields and energy as objects, etc. You're using abstractions to do physical interpretations. And abstract is the opposite of physical. And we're doing physics, we're not doing abstraction, so we're not abstracists. We are physicists, the opposite of abstracists. Okay, so here we have the stoplight. This is the answer to him. The claim of irrational mechanics is that light is stored in the medium. So they're saying that they're going to freeze a little piece of region of space, right? They're going to freeze whatever's in there, meaning atoms, right? And because they froze that, suddenly they froze the photons of light which were flying between those two atoms. So we have these two atoms, right? And the photons which are between them are frozen in midair. That's what they claim, that they froze light in the medium. Yet we can see the light trapped in there because, why? The atom is pumping that light to our eyes. Now, if you don't believe in the rope, no problem. You don't accept the rope, no problem. But under the quantum version, it's quantum jump, motion of the electron back and forth, closer and farther away from the nucleus that generates light, the energy coming out of the atom, as they call it. Okay, so even if you go with quantum, something is moving in there, and that's why you would be able to see. If no quantum jump takes place, there would be nothing to see, because now you're not receiving energy or frequency or wavelength from the atom. Okay, so if we can see the light, then light has not stopped. If you can see a little bit of light in there, light has not stopped. Even according to the religion of quantum, light is generated when the electron rises and falls from energy levels, right? If the experiment receives light from the frozen region, an atom from inside the region is sending it to his eyes. Okay? Therefore, the claim that the experiments have stopped light is a lie. Meaning, right? Let's say it scientifically. The forgers have once again falsified their results. That's what it is. Stoplight should not be visible. That's the bottom line. Okay, so here we have the experiment. I think this is the original experiment. This was done in 1998 or 1999, okay? And I think it was this lady who did it in Harvard. So listen to her. Well, this is the introduction to what she did later. The fellow who does the reporting, he explains it first. So listen to him first. Okay, here goes. So he's going to explain what they did as far as the experiment. They're going to freeze the atoms in this ultra-cold region. Okay, here goes.
Lena Howe created a cigar-shaped Bose-Einstein condensate to carry out her experiment. She fired a light pulse into the cloud. When the pulse hits the condensate, it slows down to the speed of a bicycle.
Okay, so light goes to the condensate, this cold region. Okay, you don't have to know any fancy words. You essentially send light and somehow freeze that region, and like it's frozen. Okay, and you saw how the light comes in. Now listen to her, how she freezes it. Okay, this is the lady who supposedly came up with this. Okay, here goes. Listen to her.
So the light pulse might start out being 1 to 2 miles long in free space. It goes into our medium. And since the front edge enters first, that will slow down. The back edge is still in free space. That'll catch up, and that'll create that compression. And it'll end up being compressed from 1 to 2 miles down to 0.001 micron or even smaller than that. You could say, well, we just set a laser beam into a wall and I would stop it. Well, the problem is you lose the information because it turned into heat. You can never get that information back. When we stop it, the information is not lost because that's stored in the medium. Then when we have time to revive it, the system has all the information to revive the light pulse and it can move on.
Okay? So what's the issue? The issue is they're shining a light to this region and they freeze light, but you can see that there's a little light there. Why can you see that light? And so let's go in steps here. Let's make sure we understand how light is generated, not according to my theory. Let's go with quantum. Let's go with their version, okay? Okay, here it goes. There's your atom, right? This is the atom created, the planetary model created by Rutherford and Bohr. And they've modified it nothing really in the last 100 years. They say that it doesn't orbit like that. It just bounces around different areas in the region called an orbital. So it doesn't matter. Here we made it smooth. It's just not smooth. That's all you got to think about. But the point here is when the atom falls to a lower energy level, it releases that green arrow, which is energy, which is light. And when it rises, apparently it does so again. Okay, so it's constantly falling and rising, and by doing that quantum jump, that's what creates light. So something has to be moving in order to create light. If you were to freeze that electron, there would be no light according to quantum mechanics. Okay, this is not me, this is according to quantum mechanics. So let's get that right. Okay, so this is the official version. Now, here's what this lady showed. Okay, she showed this. And you see that little light there, and you say, hold it, I can see a light there. Why am I seeing the light? I should not be able to see anything. Yeah, but they say, look, we can see the light. We've frozen light right there in that region. Well, we have a problem because, here, let's illustrate that. You have all these atoms pumping these torsion waves, transverse wave to your eyes. Why am I seeing that light if light is the back and forth, the movement of the electron back and forth from energy levels or orbitals? So something is still moving in there if I can see that red light. Otherwise, I wouldn't see the light. I wouldn't see that red light. And just in case, here it is up close. Okay, so that's what it's doing. It's got the atom has to be pumping. Okay, like I say. The electron has to be moving back and forth between energy levels to create those waves or particles. I mean, I could replace the waves with particles. We're in the same boat. Okay? Or I can replace them with ropes, electromagnetic ropes, as we say. And same thing. In other words, whatever you replace it with, that means something is moving in there if you see that light, if you see that red light. Okay, so we have a problem here because, these people are saying you can see the light, but we stopped light. So what do you mean? What is that you stopped? I mean, obviously, if I can see the light, something is moving in there, and you haven't frozen light. If you freeze light completely, you shouldn't see anything. That's the bottom line. So no, we cannot stop light at least if you see that, right? But under the rope model, assuming you could freeze the atoms from pumping. See, remember how this worked. You have the two atoms and my fists, right? And they're expanding and contracting. They're doing this, right? Expanding and contracting. By doing so, they torque the rope. Okay? Now, assuming we could freeze the atoms so they're not pumping anymore because we took them to, 0 Kelvin or whatever. Okay, so we've got very cold region. The atoms are not pumping. Now the rope is not torquing. That we can understand. But then we should not see anything. Because light does not come from the rope to your eyes. Okay, you're not going to see light. You're going to see the atoms which are sending light to your eyes. Light comes from atoms, not from rope. You can't have a rope coming from the middle of another rope. The rope comes from the atoms. So if the atoms are, standing still, then they're not pumping torsion waves to your eyes. Just that simple as that. So you should not see anything any old way you look at it. That's if we can freeze atoms to the point of them not pumping. But then if, like this lady says, that she was able to freeze light, well, did she? I mean, if light is coming to my eye, something is pumping in there. So obviously she's got a contradiction that she hasn't resolved. But they were quick in publishing it. They said, oh, this lady froze light. Yeah. Okay, and there's another issue we need to solve, and it's one that we're going to take as homework for everybody, okay, anybody who wants to deal with it. And that is that we were talking about why light travels straight, okay, and we're going to try to answer this question probably next week, okay. Today was just beyond the scope of the class today, lecture, right? But the question is, can you see light backwards? When light goes through, it's really going through a bunch of atoms in air. That's why you see the reflection. Like when you see light sideways, right? A beam of light, such as a laser pointer, a strong laser pointer, and you see the red light, for example, right in front of you, like a straight line. Why are you seeing it? Well, because that light is stimulating every atom that's in that line of sight, right? If you were looking through at the same parallel to the laser. But why can you see it perpendicular? Because it's sending light to your eyes through all the atoms in the air that are connected to your eyes. That's why. Okay, so you need a mediator in order to see. You need atoms for reflection or refraction, right? Or diffraction, if you, any of them, right? You need a mediator. If there's absolutely nothing, you would not see it sideways. The only way you can see sideways is something, if there's an atom there that is relaying, light to your eyes. But then what happens when you're behind the laser, right? Can you see it from an angle? Yes, you can. You don't see it as good as if the laser's pointed directly at your eye. So it's much more intense going into your eye if it goes straight into your eye than if you're seeing it from the side or from an angle. And the question is why? Doesn't every atom along the path send light in every direction? And this is the same for any, I don't care if you believe in quantum mechanics, you want the rope model, anybody has got to answer this question. Why does light come out of an atom in every direction, right? Because it's doing this quantum jump. And why can I see it more in the direction in which the light is being sent, right, by the laser than from the side, from an angle? Okay, so that's the issue. That's the question in front of you. And so here, I'm going to show you what I'm talking about here. You see light going out there from a source to some target, okay? And the question is, you have this light going in every direction. I only put 2 atoms there, right? Any atom in there, it will send light in every direction. Backwards, for example, or frontwards, but not along the main beam. And so the question is why? Why do we see less of the light behind than in the direction in which the beam is pointed at? Okay, so that's the $1,000,000 question. Okay? No math. Just answer the question, right? We don't want any equations. We don't want any numbers. We just want to know the physical cause. Why? I think I have. Here's my laser pointer. Here you have light. Okay, I hope you can see that. Okay, and so the question is, you can see that there, but see sideways you see much less. Not as brilliant. And the more I turn it, the less you see. It's there that you see it a lot. And the question is, why do you see more in the direction of light and not to the sides? If every atom along that beam, right, along the ray, every atom there is shooting light in every direction, is relaying the light in every direction, refracting it, reflecting, etc., right? Why shouldn't you see the same amount? And that question, again, is for quantum, whether you do waves or particles, or for the rope. For all proposals, the question stands, okay? With that, I'll see you next week. But before I do, if anyone has questions, go ahead and shoot. I'll give you 10 seconds. That's how long it takes for me to receive and, I guess, transmit the answer. So give you a chance there. Okay. Well, I guess I'll call it a day and we'll see you next week.